Hello, everybody, and welcome to this new seminar for the I'm series. And together we have with us a young and brilliant scientist, Petar Veličković. Petar Veličković is a staff research scientist at DeepMind, affiliated lecturer at the University of Cambridge, and an associate of Clare, Cambridge. He holds a PhD in computer science from the University of Cambridge, Trinity College, under the supervision of Italia. Petar's research concerns geometric deep learning, devising neural network architectures that respect the invariances and symmetries in the data, a topic he has co-written a proto-book about. For his contributions to the area, Petar is recognized as an Ellis Scholar in the Geometric Deep Learning program. Within this area, Petar focuses on graph representation learning and its application in algorithmic reasoning and computational biology. In particular, he is the first author of Graph Attention Networks, a popular convolutional layer for graphs, and Deep Graph Infomax, a popular self-supervised learning pipeline for graphs featured in ZDNet. Petar research is being used in improving the travel time prediction in Google Maps, featured in the CNBC and Gadget, VentureBeat, CNET, The Verge, and ZDNet, and guiding the intuition of mathematicians towards new top-tier theorems and conjectures, featured in Nature, New Scientist, The Independent, Sky News, The Sunday Times, and The Conversation. And now, we give our welcome to Petar. Welcome, Petar.
All right. Thanks so much for the kind invitation and for the great introduction, Italia. Hi, everyone. My name is Petar Veličković, and I'm a staff research scientist at DeepMind and an affiliated lecturer at the University of Cambridge. And today I'll be talking to you about some of our recent work on applying artificial intelligence and how it might be applied within the scope of pure mathematics research. This is work that I've done in collaboration with a lot of really fantastic people, both at DeepMind and at the universities of Oxford and Sydney, and they have all been listed on this slide, and I'll probably make references to a few of them as we go along today. What I really want to be kind of seeding in you as the basic question to be asking and that we will be discussing today is quite simple. Can we use machine learning to discover new structure in pure mathematics? So this is our main guiding question that we'll be thinking about throughout the talk today. And the reason why we believe that this is a potentially very powerful paradigm is coming from the fact that the practice of performing mathematics and doing mathematical research is often much more intricate than just simple following of logical rules. And perhaps there's no better example of this than the mathematician that you can see on the slide in front of you, Srinivasa Ramanujan, who often was able to come up with these pretty fascinating theorems and conjectures which appeared to have basically materialized out of thin air. So in many ways, the great advances in mathematics are not only made by blindly applying logical rules, but also by a very creative imagination process. And perhaps one of my favorite examples of this, and which I often used as like a guiding light as we set up on investigating this intersection of AI and maths, is the work of Johannes Kepler. As you probably might know, Kepler has discovered the key laws of planetary motion in the solar system. And the way in which he arrived at these laws of motion is by painstakingly studying years and years of astronomical data and observations. And based on that data, he was able to spot regularities in the trajectories of various planets. And when he finally managed to detect a very stark regularity in the movements of the planets, he is infamously quoted as saying that he first believed that he was dreaming. So if you think about it, mathematics is not just about a set of axioms and applying rules, but also about creative imagination and about dreaming. So the main question that we want to ask ourselves is, can machine learning and artificial intelligence somehow help us in the process of doing mathematical research by automating exactly this part that helps you focus your imagination, your creativity? And in a way, what we're doing is just going to amount to some kind of pattern matching on mathematical data. And it should be stressed that we are not the first team ever to try doing something like this. In fact, the use of computational power to detect mathematical patterns dates back centuries ago. And in fact, even before the advent of computers, some of the most important results, like, say, the prime number theorem from Legendre, was derived by basically manually looking up prime tables and then trying to manually study the prime numbers and detect regularities between them. Once computation became more readily available and people moved away from manually computed tables, this obviously accelerated the kinds of results that people were able to show. And perhaps one of the most famous examples of this is the BSD conjecture from Birchins, Swinnerton, and Dyer, which is one of the Millennium Prize problems. And there, computers have been used to compute some of the examples under study in this conjecture, but the pattern was still detected manually. So what we really want to show is possible with our work that we have published last year is that you can use computers not only to compute examples, but also to detect and refocus the attention for the pattern detection part too. So to what extent have we been successful in this? Well, this is generally how we propose to do this. So we propose this particular algorithm for mathematical discovery, which is powered by artificial intelligence. So how it works roughly is a mathematician might hypothesize that two quantities are related. So imagine you have some object z, and based on that object, you have two different quantities you can compute, x of z and y of z, and you believe that there is some kind of relationship between them, or you just want to test out whether that relationship exists. So you believe that there is a function that maps x to y. You can then use this knowledge to generate a paired data set of x's and y's based on some sampling distribution z. Based on that, you can train a machine learning model to predict y given x, simple supervised learning. And sometimes we will see throughout this talk just the existence of a supervised model that achieves such a strong accuracy can give a lot of encouragement to the mathematician that this is an area worth investigating. But oftentimes it's not enough, and we often need to somehow interrogate this learned machine learning model to find interesting patterns via what we call attribution or saliency. So some kind of model diagnostics for supervised learning. And now, based on the fact we have a strong predictive power and we've detected some possible patterns in the data, the mathematicians can then take all of this data together to conjecture a candidate function of interest. And sometimes this is enough to go away and prove a theorem based on it, but sometimes the conjecture candidate leads to rinsing and repeating this process with sampling new data, reformulating hypotheses, and so on and so forth. And we'll see many examples of this back and forth process throughout this talk today. So I must stress that when we set out to do this work, we reached out to a lot of mathematicians and we asked them what their thoughts were. Like, could machine learning truly automate this creative part of the process with the pattern hunting? And I must stress that in many cases, the responses we got were reasonably negative. Like, mathematicians genuinely did not believe that much that something like this would be possible. Well, after 2 years of work with some of the top tier experts in knot theory and representation theory, we have in fact been successful at using machine learning to help guide the pattern hunting aspect of deriving conjectures and theorems. And the significance of our results in two distinct fields of mathematics has been high enough that the journal Nature has decided to display it on the cover a few months ago. And besides the fact that it warranted the cover, I also thought that it might be useful just to give a contrast to what the reviewers of this paper actually said, and specifically the reviewers that were from the experts in pure mathematics and in the areas that we studied. And just as a sample, the reviewers generally found that this paper marks the beginning of a new phase in use of computers in mathematical research. They cannot imagine a mathematician not using a method like this if it was available, because not using it means progressing much more slowly. And specifically, our separate contributions to representation theory as well as knot theory have been judged as likely publishable in a top journal in the respective area of mathematics. So beyond just showing that there is an interesting method to do pure mathematics research by computationally detecting patterns, we have also come up with several very interesting standalone contributions to mathematics, which are now under review in the respective journals. And specifically, we also put out the two specific contributions as separate mathematical papers, which you can now find on the archive. And specifically, the two main areas that we studied in this work are knot theory, together with Mark Lackenby and Andras Juhas from the University of Oxford, and representation theory, which we worked on with Jordi Williamson of the University of Sydney. Okay, so if you are a mathematician or are interested in a lot more mathematical detail about what we've been able to achieve, these two papers are probably a really good starting point. But what I'm going to do for the rest of this talk is just dive into roughly how the machine learning was part of the whole process in these two papers, and try to also give you a bit of an insight on how it felt to collaborate with mathematicians at this particular exciting interface. So without further ado, I'll dive first into the knot theory example, which was primarily led by Alex Davies and Anna Tomashev on DeepMind's side in collaboration with Andras and Mark from the University of Oxford. So this was work that I was less directly involved in, but it also involves a somewhat simpler example of a machine learning model and just how impactful even a simple intervention can be in these cases. So it's a very good starting example to give. So if you haven't seen knots before or haven't been too familiar with knot theory before, here's just a quick refresher of the main object that we'll be studying. So knots are effectively very related to the knots you'd find in the real world, only that in this case, the loop is closed. So you have some kind of a closed loop that crosses itself and it's embedded in a three-dimensional space, and you want to analyze some kinds of interesting properties of that closed loop. And specifically, one of the things that's very interesting for knot theorists to study are so-called knot invariants. Because you can observe a knot from so many perspectives, you can look at them as algebraic objects by basically performing some kind of algebra over the different crossings of a knot. So there are ways to analyze its structure from the point of view of algebraic invariance. But also they are, as I said, this closed loop embedded in a three-dimensional space, so you can naturally also attach a geometrical object to it and study some interesting topological invariance over that knot. And prior to our work, there have been very few known connections between these geometric and algebraic structures of knots. So obviously, some people were hoping that this connection would exist, but it hasn't been very decisively shown until our work. So the main question that we set out to answer, guided by the advice of our mathematician collaborators, is can we derive a relationship between the geometric and the algebraic structure of a particular knot? So this sounds like a nice setup for our supervised learning problem. And just to give you a feel for what these different geometric and algebraic data looks like, here I've given a very simple table where I have these three example knots illustrated on the first column. And now for every single one of those knots, you can compute using various knot software, some interesting geometric invariants and some interesting algebraic invariants. It's not that important for our discussion what these invariants actually are, but what's more important is to see that there is a big variety of different data types that happens here. So you have some real numbers, you have some complex numbers, you have polynomials, you have integers, right? So there's a big variety of different kinds of data you could put in a machine learning system like this. And there's different interesting questions on the representations. But our question here is to demonstrate some kind of relationship between the geometric and the algebraic, right? So what we need to do is we should pick some quantity to be predicted on the right-hand side by a machine learning model, and then predicted based on everything else. Now, as you know, in machine learning, classification problems are generally reasonably easy to set up. And that's why if we have anything that's integer value, that is probably a good idea to focus on that. And as you can see, we have a very nice integer property on the right-hand side, which is the signature of a knot. So basically that guided the design of which task we were going to look at. So we want to predict the signature, which is an integer and therefore can be represented as a classification problem, based on all of the data that's given in the geometric invariance. So we train a simple deep neural network, like a multi-layer perceptron, to just predict the signature given all of the geometric invariance. Okay. And what did our model learn to do? Well, our model worked quite well. So it turns out that the value of the signature, which, as I said, is an algebraic invariant, can be reasonably well predicted from the geometric invariance. In fact, the predictions of our model had a coefficient of determination, which was about 0.94 r squared. So there is a pretty good correlation between what the model learned to predict and what the actual signature is. And this, as I mentioned, already gave our collaborators a lot of confidence that probably there is some very intricate connection going on here. And this led them to believe that we should continue working in this direction, and hopefully we will discover something interesting. Now, what do you actually look at is the bigger problem here. So we know there's a connection, but where is it? And it turns out that machine learning can also help here to an extent. As I said, we need to employ some kind of interrogation technique to ask the model what were the parts of the input that you found most important when you made this machine learning inference decision. And it turns out that for these simple MLPs, even though machine learning models nowadays tend to be black boxes, some very simple interpretability questions can still go a long way. So one simple thing you can do here is what we call gradient saliency. So you literally just, since this model is fully differentiable from the input features to the output of the signature, we can predict which inputs cause the biggest change in the gradient or receive the largest gradient at every inference step. And the results of that first analysis can be seen on the right-hand side. So, it doesn't take a very skillful mathematician to notice some very obvious outliers here. So it seems like if you look at it properly, some geometric invariants like the meridional and the longitudinal translation seem way more important than the others. So we can now go away and tell the mathematicians that, hey, these two quantities, the longitudinal and the meridional translation, are likely very important for the relationship with the signature. And just using that piece of information and a bit of algebraic manipulation, our collaborators have been able to come up with this quantity, which they call the natural slope. And it's very easily definable with the existing quantities, but it wasn't previously importantly studied enough to warrant being put as a default element of knot tables. And when you define a slope of a knot as this simple sum of the real parts of the meridional and longitudinal translations divided by the squared norm of the meridional translation, you end up with a quantity that almost very nicely linearly correlates with the signature. So here you can see a plot of slopes to signatures for different knots. And you can see that there is a very clear linear relationship going on. In fact, once again, doesn't take an expert in data analysis. You can just look at the range of the x and y axes to say that there is roughly a relation between slope and 2 times the signature, right? And obviously, there is some error term going on because it's not a perfect linear fit. So the remainder of our efforts basically boil down to, can we somehow hammer down this error term? And our collaborators have been able to make a first guess at this signature slope conjecture. So they assumed, once again, that the slope is roughly 2 times the signature, and the error in this estimation can be upper bounded by the square root of the volume of the knot. And this was the first assumption, which seemed to work really, really well for all of the knots we had in our initial data set. So it's a conjecture that seemed to hold. However, there is one very important thing that always must be kept in mind for these kinds of problems, and that is that how successful a machine learning model really is at fitting your problem will largely depend on the distribution of the training data that you give to it. And in this case, it turns out that it's possible to construct a counterexample to this conjecture that we just posed. And specifically, you can use this very twisted class of braided knots, one example of which you see on the right, to push this upper bound to a breaking point and actually cause the conjecture to fail. And what's important to note is that these braided knots were not part of the data set that we used to train our model, or they were very weakly represented in it. And as a result, our model hasn't kind of learned to pick out this particular special case. So this is one example of a back and forth where we suggested something to the mathematicians. They discovered this very nice property, the natural slope, and they almost got a provable conjecture, but something's still not quite right. But in this case, it turned out to be quite sufficient to just go back to the drawing board. Like, here's exactly the same plot of the saliency of the different geometric properties that I told you about. We already used the first three to define the slope. And if you look at the remaining quantities, once again, not too hard to spot that there does exist a second cluster of quantities: the short geodesic, the injectivity radius, and the cusp volume. And these seem to be likewise significantly more important than the other ones. Okay, so maybe we can make a more tighter upper bound or more proper upper bound if we use some of these different geometric invariants. And when we gave these suggestions to our collaborators, eventually they have actually been able to come up with a formula, which is just a different upper bound that now also features one of these three quantities, the injectivity radius. And you can see the injectivity radius here on the right-hand side. Which actually our collaborators have been able to prove. So this is a theorem which we have been able to successfully show in our work, which came about as a direct result of the back and forth with the machine learning model. And this constituted our first significant result in the area of knot theory. And specifically, if you look at the cover of our Nature work, you will see this equation kind of highlighted in bright lights as maybe one of the first theorems effectively proven with artificial intelligence guided intuition. Okay, so hopefully this gives you a very clear example of how even with a very simple machine learning intervention, we are able to help mathematicians synergistically come to conclusions about previously unsettled relationships in areas as intricate as knot theory. Now I will switch gears completely and talk to you a little bit about the second branch of this work, which corresponds to our work on representation theory. This is a project that I have undertaken together with Charles Blunder, Lars Pusing, Alex Davies, and our collaborator Jordi Williamson from the University of Sydney, who's one of the world's top experts in representation theory. And as I said, this is a project where I've basically been involved from start to finish as one of the lead modelers on the machine learning side. So I have a lot more insight that I can share about how the process went in this particular case. And conveniently enough, because the model for representation theory project is much more complicated than the machine learning model in the knot theory, which was just a simple multi-layer perceptron. Okay, so one question you might ask yourselves here is, where do we even begin? What I'll present to you here, I'll have to write a disclaimer, is a bit of a streamlined view of a year and a half of research. So there's a lot of interesting theory and experimentation I'm not telling you about here, but I have to do this to make the talk more clear and flow better. So I'll only condense the part of the theory that's necessary for you to have a basic understanding of the problem. And I must stress also how important it was that at the beginning, we from DeepMind knew next to nothing about representation theory, and our collaborator Jordi wasn't that familiar with machine learning. So many of our early interactions have really been just like 2-hour-long lectures and deep dives to get us both to understand the side of the other. And as a result, it was a very nice learning interdisciplinary experience. But most of the machine learning work that we've done in between, so most of the models we trained, the results we got, almost everything that happened along that journey was impactful to the final result we made. So one thing that's very important to note is that for the most part, the machine learning experiments I'll show you here are not cherry-picked, but instead they represent a very direct, straightforward route of how we went from start to finish in this particular project. And here's just a few snapshots to give you a feel for how these representation theory lectures looked like. Obviously, this collaboration started around the beginning of the COVID pandemic, so none of this was in person, and we had to rely on modern technology to basically go in intricate detail about the various objects that we're studying and the interesting algorithms for computing data over them. And we've been very fortunate to have a very dedicated mathematical collaborator who, as you can see on some of these slides, very carefully illustrated for us the specifics of the objects that we're dealing with so that we can represent them more effectively in machine learning systems. And there have been a lot of very useful definitions of objects in the meantime, which also we've tried to align as good as possible with established terminology in machine learning. So the main object that we're studying in the representation theory branch of the project are so-called symmetry groups. They can be roughly described as groups of transformations on an object that leave that object unchanged. And specifically, the group we will be focusing on, and the one that is the most important here, are permutation groups, which for those of you who have seen graph neural networks before, you will probably know that permutation groups are also the essence behind how we build modern-day graph neural networks. So there's a lot of correspondence to modern-day approaches to geometric deep learning as well. But basically, all we're dealing with here is a permutation. So we have a collection of, say, 5 objects, and one permutation of those 5 objects changes the order in which you see them, but it doesn't change the underlying set. And we can usually numerically code these permutations like 3, 2, 4, 1, 5, as you see on the right-hand side. All this says is that basically object A ends up in the 3rd slot, object B ends up in the 2nd slot, C in the 4th slot, and so on and so forth, right? So these are very simple symmetry transformations that basically form the basis of a lot of modern-day group theory. Specifically, within the context of symmetry groups, we are studying a special kind of symmetry group known as the Cox Center Group, which the permutation group is an instance of, but the main property that these groups have is that you can fully describe them in terms of a subset of the transformations, which are known as reflections. And the specific instance of reflections for the permutation group are just single swaps. So swapping 2 elements, but leaving all the other ones unchanged. And as you might know, swapping is the basis behind the sorting algorithms. So if you're only allowed to perform swaps, if you can compose them with one another, you can end up deriving any permutation you want. So here's just a simple example for the 4-element permutation group, also known as S4. In the 4-element group, there are exactly 6 different reflections. And here you can see all 6 of them lined up one next to each other. So in each one of these, we pick 2 elements and we swap them and leave everything else exactly the same. Okay. Now, specifically within this context, we can also talk about what's known as a generator of the group. So a set of these transformations from which you can recover the entire group just by composing. And for the permutation group, you can actually recover everything by just swapping adjacent elements. Once again, algorithms like insertion sort and bubble sort are very clear examples of this, where you always swap adjacent elements. So when you have the 4-element permutation group, out of those 6 reflections, there exist 3 simple ones, 3 generators: 2, 1, 3, 4, 1, 3, 2, 4, and 1, 2, 4, 3. So swapping the 1st and 2nd, the 2nd and 3rd, and the 3rd and 4th element. Based on these 3 special transformations, you can recover the entire symmetry group. Okay. Now that we have this basis, the mathematical foundations of the objects that we're studying, we can talk about our key players. So, first of all, we can think of every permutation as a node in a graph, which we will call the label Bruja graph. And obviously, if you're going to have a graph, you also need edges between the different nodes. So in the case of permutations, when do you draw an edge between 2 permutations? You draw it if you can recover one of these permutations from the other by performing a reflection. So if you can get one permutation from the other by just doing a single swap somewhere, then you link them with an edge. Now, this graph is typically directed, so we need to have some way of orienting it. Obviously, if I can get permutation A from B by swapping, I can get B from A by doing that same swap again. So this graph would otherwise be undirected. But we can orient it by using some measure of how disordered the permutation is. So we put the identity, the 1, 2, 3, 4 permutation, which doesn't change anything, at the bottom of this graph. And then we put on the first level all the permutations that you can reach from the identity by just performing a simple reflection, so all adjacent swaps. And then we can proceed inductively by performing adjacent swaps on those and so on and so forth. And we orient our edges in the graph such that they always point towards the permutation which is higher in the graph. So just to give you a visual example of what I just said, here is what a labeled Bruja graph might look like for the permutation group of 4 elements S4. So as you can see at the bottom, you have 1, 2, 3, 4, the identity permutation. In the first level, you have the adjacent swaps, 1, 2, 4, 3, 1, 3, 2, 4, and 2, 1, 3, 4, and so on and so forth. We gradually build up this graph by performing adjacent swaps. And you also have various edges in this graph, which are either solid or dashed. The solid edges are the simple reflections, so adjacent swaps, and the dashed edges are not simple reflections, so they are swaps, but they are not swaps of adjacent elements. So this graph gives you a very rich representation of what's going on inside the permutation group with respect to these specific generators. And now we can talk about how observing these objects leads to one of the most important conjectures in representation theory, which is known as the combinatorial invariance conjecture. So how do we go about this? First, we take any 2 elements in a Cox Center group. So for example, if we're working in the permutation group, this means choosing 2 permutations. And now based on these 2 elements, I can define 2 objects. The first object is the Bruja interval, which is the subgraph of that graph I told you about before, which only contains the paths between these 2 nodes and also drops all of that nice labeling information that I gave you before. So you don't know anymore which node is which permutation, which edge is which swap, and so on. All of that information is dropped. You just have the graph structure. So the Bruja interval is something that combinatorially grows very fast because obviously permutation groups are on the order of n factorial elements. But it's very easy to describe, like these subgraphs containing all paths. But on the other side of the picture, you have the Kazhdan-Lusztig or KL polynomials, which can also be defined for these 2 objects. They're notoriously tricky to properly explain and characterize, but basically, they are a polynomial with integer coefficients. Now, one very important point, which I will stress again, is that this Bruja interval is now unlabeled. So we took 2 permutations, we took the subgraph of all the paths between them in that graph I showed you before, and we dropped all the information from that graph. So we don't know which node and edge belongs to which permutation. It has been a long-standing conjecture by Lusztig and Dyer that these 2 objects, the interval and the polynomial, can be fundamentally related to one another, i.e. that you can compute the polynomial from the interval. And this is known as the combinatorial invariance conjecture, which has stood unattacked were virtually unattacked for 50 years. And I'll try to illustrate some possible reasons for why it has managed to resist attack for so long. So the general question that we have here is we have these different kinds of subgraphs of all the paths between the 2 objects we chose, so the Bruja interval on the left, and the coefficients of this polynomial, KL polynomial, on the right-hand side. Okay. So the reason why I think it's very tricky to talk about how to map one to the other is that the patterns in this case that might be interesting for a mathematician to investigate emerge only when the input graph is already very, very complex. So the reason why this happens is that for most of the Bruja intervals, so for most of these graphs that you can easily generate, the KL polynomial is actually super simple. It's either 1, Q, or 1 plus Q. So reasonably very simple polynomials. And remember, these polynomials can grow to arbitrarily large powers. You could have Q squared, Q cubed, and these kinds of things, right? So in the permutation group S4 that we talked about before extensively, so 4 elements, all of the KL polynomials are trivial except for this particular one, this Bruja interval known as the crown, which gives you a polynomial of 1 plus Q. So this is the only non-trivial example in the group of 4 elements. And here I've just added labels to the different permutations so that you can like visually see how this graph is constructed. But in reality, that information is not given to the machine learning model. So we just have the graph structure and nothing else. And now you might be asking, when does Q squared appear? So that's the first next biggest power, right? Well, here you go. This is how big this graph has to get before you see a coefficient of q squared in the polynomial. So this here is one of the easiest examples. And already this example is very tricky for a mathematician to look at, observe, and analyze, right? So it's very difficult to look at even these simpler examples and decide what's the interesting structure hidden inside these graphs that cause the q squared to appear, right? So this is why I believe manually attacking the pattern hunting problem is likely doomed to fail for this particular task, because the complexity of the inputs grows much faster than the complexity of the outputs. So how do we manage to deal with that? Well, we propose the use of machine learning to potentially help give the mathematician a magnifying glass that can very carefully focus on some parts of this graph and hopefully make this task a little more tractable. So we want to train a neural network to predict the coefficients of the polynomial from these graphs. And this is just to give you an example of what the training data looks like. So here is one particular unlabeled Bruja interval for the permutation group of 6 elements, which gives a non-trivial polynomial of 1 plus q squared. And once again, we don't have any information on what these nodes and edges are. All that information is dropped. We just have the graph structure, and that's it. And we have to predict the different integer coefficients of the polynomial on the right. And here's one example where another one of the smaller examples where we have both 1 plus 3q plus q squared, so a more complicated set of coefficients. As you can see, the graph has already become very, very complicated, and we're still in the group of 6 elements. So there is a lot more complexity coming our way after this. Now, a question arises. So we know we want to build a machine learning model mapping these Bruja intervals to the integer coefficients of the polynomial. But what's the machine learning model we should use to predict this? Well, what helped us there is basically the fact that there exist algorithms that will compute the scale polynomial if we have that privileged information we dropped. So if we have the labeled Bruja graph, we can compute the scale polynomial from it. And our mathematician collaborator was very kind to show us these algorithms that can compute the correct solution given all the privileged information. And on the right-hand side, you can see some of the equations that they wrote for us. And basically, to us, as some of us have had some experience with graph neural networks, these equations felt a lot like standard message passing equations with the ReLU activation. If you see this tau symbol here, it basically takes some intermediate polynomial based on a sum of all the neighbors in the graph, and then cuts out all the polynomial elements that have negative powers. So it felt a lot like a ReLU activation, right? Like everything that's negative needs to get cut off. So this basically guided our decisions to employ graph neural networks with ReLU activations and task them with doing graph classification. So we are given a graph as input, which corresponds to the Bruja interval. And we have a classification problem on predicting some coefficient of the KL polynomial. So the hypothesis behind building a model like this is basically that our graph neural network should be able to recover some relevant parts of these equations just by looking at the structural properties of the graph, which is basically what the combinatorial invariance conjecture is all about. So even if I drop all that privileged information, you can still derive everything that's necessary just by staring at the graph isomorphism class. Okay, so we built a data set of all the Bruja intervals up to the permutation group of 9 elements, when after that, the factorial kind of starts to bite you. And we trained our graph neural network to predict the individual KL polynomial coefficients. And this is the performance, the accuracy that we achieved with our very first model. And you also have baseline performance of a random chance guesser of the coefficient. And you can see that significantly, our first graph neural network has learned to predict all of these different coefficients with a much higher accuracy than chance. So this was, in and of itself, a super encouraging result for our collaborator, because previously we had an algorithm to compute the coefficient of Q and not much else. So all of these new Q powers were treading new ground. So naturally, we wanted to ask the question of what has this graph neural network learned to do? Are there some interesting subgraphs in the input that we should be looking at? And well, we tried to use our simple saliency methods to get some interesting subgraphs, like the nodes and edges that receive the highest gradient in the message passing procedure. of the graph neural network. And well, these are the kinds of graphs that it produced. To us, a lot of this looked like nonsense. Like we couldn't really make sense of what was going on here. But we still felt like trying, right? Maybe we need a better explainability method, but maybe this was already potentially useful. So we sent all of these graphs to our mathematician collaborator. He looked at them for 2 weeks or something like that, and basically he was able to tell apart the signal from the noise. So he was able to figure out that hidden inside all the spurious correlations in these subgraphs, there actually is a hidden substructure that feels very similar to something that he has seen in prior research. And that structure he called the dihedral intervals. So after looking at these subgraphs for a long time, Jordi was able to figure out that often they contain nodes near the bottom of the interval. So these nodes at the bottom here that I've highlighted. And very often they picked out these interesting diamond-like structures in the edges. So that led them to the discovery of the dihedral intervals and diamonds. Well, not discovery, these structures were already known before, but they were studied before, so there was a hypothesis that maybe these structures were quite critical to the final formula that the neural network learned to detect. So, okay, let's try to train our graph neural network again with extra features telling the graph neural network where these diamonds are. So just feed that as extra input features to the graph neural network. Is this node in a diamond? And so on and so forth. Is this edge in a diamond? And so on. Well, it turns out when we added that extra structural feature, our accuracy increased dramatically. So with these extra features, we've now been able to fit every single q power up to q to the 4 with more than 95% accuracy. So clearly this came as a super encouraging result to us, because it showed not only through this back and forth process that there is definitely a very interesting connection between the graph and the polynomial, but also it validated directly the claim of our collaborator that these interesting substructures were likely highly relevant in the final formula. And the crucial observation that allowed us to kind of go full circle and cement all of this in is to study which types of edges were most important for the graph neural network to use. And it turns out that here you have, for the specific case of S9, so the group of 9 elements, if you remember, every single edge in the graph corresponds to a swap. So we can check how often does the model favor swaps of A and B. And here blue means more important. So as you can see, the model really tends to favor these so-called extremal reflections, where element 0 is swapped or where element 8 is swapped. And this observation turned out to be critical to the final discovery. And one of our mathematical reviewers also highlighted how important they found it. So to them, the feeling that these extremal reflections seem to play a crucial role is something they would have expected only from a handful of great experts in representation theory. And it was such a human suggestion, quote unquote, that I'm quoting the reviewer here, it gave them goosebumps. So these kinds of analyses, even with simplified machine learning saliency, can lead to potentially, goosebump inducing outcomes. So clearly this was a great win for us. And based on the fact that there are dihedral intervals, the diamonds, and this knowledge of the extremal reflections, our collaborator was then able to propose this hypercube decomposition where essentially you decompose the initial graph into two parts, an inductive part, which you can solve by induction, and the part which looks like a hypercube in n dimensions, where you can proceed to resolve the missing residual part of the formula. And in fact, Jordi was even able to prove a theorem that every single Bruja interval has one of these hypercube decompositions that allows you to directly compute the polynomial. So this, to some of you, might feel like we have resolved the combinatorial invariance conjecture, but it's not quite there yet, because the theorem says that a hypercube decomposition must exist, but it doesn't tell you how to find it, because there could be many hypercube decompositions and not all of them are guaranteed to give you the correct solution, so you wouldn't know how to find the right one necessarily. We just know that a right one must exist. Well, we then set out to find how often would a wrong hypercube decomposition happen. And at least for all the symmetric group Bruja graphs that we sampled from groups up to S9, we haven't been able to find a counterexample. So we actually further conjecture that no matter which hypercube decomposition you take, you will be able to use our formula to get the correct outcome. And if this was true, this would settle the combinatorial invariance conjecture for symmetry groups at least. So at least our computational evidence says that this is possibly true, and Jordi left some hints in the mathematical paper on how a possible proof to settle this might proceed. But basically, using this extensive back and forth, we now have a brand new set of structures for analyzing this particular problem, and much more advanced than was made in the previous 50 years by going on a completely different route of trying to demonstrate that there is a formula for computing this polynomial by looking at this graph. So hopefully these two parts give you a good feel for the significance of some of our results and why it might be a good idea to have an even stronger interaction between pure mathematics research and machine learning in the future. I'll just like to quickly outline a few takeaways, and then we can proceed into Q&A. So what are some of the main takeaways I'd like to note? First, even simple machine learning interventions, so a simple MLP with simple gradient saliency analysis, can have potentially large impacts in mathematics. So mathematicians are not just theorem provers. It is possible to take these very simple cues, and based on these simple cues, they can go away and build an entire complex theory of what happens next. So, like, don't dismiss that you might contribute to this method just because the machine learning models you work with are too simple. Sometimes simplicity is all it takes. We have some thoughts on when is our method particularly appropriate, but generally, if you can build large quantities of nicely labeled data of X and Y pairs, and also if it's possible that the structures inside the problem get complicated only after they get very big, so it's not easy to analyze them manually, then our method might be particularly appropriate. In my opinion, there's many areas of machine learning that will need to improve as a direct consequence of continuing our work in some directions. I think explainability is the top one. Even though we managed to get away with really simple explainability techniques in this paper, I would like to wager that we got really, really lucky. And in the future, especially as we analyze even more and more complex mathematical objects, we might not get this lucky. So we need to get much, much better at explaining why neural networks are doing the decisions that they're doing, at least in this nice noiseless regime, basically. And further, because mathematics is packed with exotic objects that we don't encounter normally in the real world, areas such as geometric deep learning, which I have co-propelled alongside Michael Bronstein, John Brunner, Taco Cohen, and others, could be particularly critical to improve going forward as we start to discover more and more interesting objects that we need to just know how to build a machine learning model for. So if it's not just a simple graph or sequence or grid, we might need some more complicated ways of dealing with it. And lastly, I think there is a lot of power in just initiating a lot of very useful collaborations between machine learning researchers, engineers, and mathematicians. And as I said, even simple interventions can be very useful. And if you want to get a better feel for how we were using these methods, we have actually released all of the source code of our experimentation for both the knot theory and the representation theory project in a collab that you can easily run even without a GPU. So if you're interested to learn more about it, just feel free to go to this GitHub link where you'll be able to access all of our code. And lastly, I do realize that the seminar I'm speaking to covers not just machine learning practitioners, but also mathematicians. And the account I gave you today is largely my personal account as a machine learning researcher. But if you're a mathematician, or you just like to know a bit more about how the mathematicians saw all of this, our collaborator from representation theory, Jordi Williamson, wrote this really fantastic article in The Conversation, which I think is a fantastic read, even beside the point of getting the mathematician's view closer to us. But in its own right, I think it's a very good read, so I would highly recommend it. And that was actually my last slide. I would like to thank you very much for inviting me and for listening. I'd be very happy to answer all of your questions that you might have online or offline. I've left my email and my social networks here if you'd like to reach out post-talk. And once again, to give a shout out to all of my great collaborators from both DeepMind, Oxford, and Sydney, without whom this work would not have been possible. So on that note, thank you so much, and happy to take questions.
Thanks, Petar. Thanks very much for this, I think, enlightening talk on the. I think it's just it's innovative. You just scratch the surface of, I believe, of what can what can come next. I mean, you opened a door and gave us some contribution, some I mean, a large contribution to this. And with respect to this, what do you think that? I mean, you already answered, but I mean, the graph structure that you feed to the model in the second scenario, the second problem that you mentioned, do you believe that is GNN are the usual the top you can use, or is there any other model approach that can help get better results with respect to the second?
So I think that's a very nice question, and the answer to it depends on what you consider a graph neural network. I personally have a very wide-reaching view of what a graph neural network is. Like, if it conforms to a specific set of message passing equations, to me, it's a graph neural network. Or if it can be expressed in that set of equations, it's a graph neural network. And in that particular framing, there's not a lot of models you cannot express as a graph neural network. So maybe to give a more nuanced answer to your question, I don't think it's possible to do particularly better, but it is possible to constrain the graph neural network to be more mindful of the inherent symmetries of the objects that we're dealing with. So one specific thing that we're dealing with Bruchheim intervals is that they're basically representing a partially ordered set or a pose set. So if you could build a graph neural network that was particularly well apt at dealing with pose sets, that kind of model would have performed better than just a graph neural network that's expecting an arbitrary graph. And there do exist a lot of interesting symmetries in pose sets, and I think there's some efforts recently from machine learning researchers trying to deal with dealing with these pose sets. So yeah, that's one example of how you might improve further.
Okay, but do you agree that these let's say back and forth approach is just at its beginning? I mean, the contribution that machine learning and AI in general can give to the mathematician, the huge mathematician universe can be very large. I mean, I just can't start thinking of any other application that
yeah. So yeah, it's very much in its inceptive days. I mean, as I said, at the beginning, we had a lot of skepticism. People just were not convinced that this could lead to anything. Now I think we're at a point where much more of the community is convinced, and we had a chance to have some great conversations with some mathematician experts from various fields. So I, in many ways, believe that we picked these two specific areas because we've been able to work with experts in those areas, and they helped us find the right problems and convert our results into outcomes. But it's really just the beginning. We want to get it to a point where, in principle, anybody could be able to use it if their problem is the right fit for it, even without the machine learning team to collaborate with them, right? So there's a lot of work to be done before we can get there. But that's where we would want to be, right? Empower everyone to have impact with machine learning. Yeah.
Okay, I think there's one online question by our colleague Vincenzo. I'm not sure if he's already, if he could enter the video. I don't know. Okay. No, okay. Yes, he was not able to get online and ask the question himself. Yes. There's another comment. Sorry about it. Okay. So there's a question. Yeah, by Nicola Polonia. I'm reading it for the sake of those who cannot read them. This looks great. However, don't you see any danger? After all, the hypercube conjecture might be false, and your misdrive efforts in this way. So, can these tools approach take you to the wrong side of the
Okay,
solution.
so this is a very important question, which I'll try to approach it from a various set of points. So first of all, for the specific case of the hypercube conjecture, we actually have a theorem which says that there must exist a correct one. So our efforts were not misdriven in that sense. We actually have a provable theorem that says that, there exists a correct one. We have, the part where we tried in many cases to come up with a counterexample and we were unsuccessful to find one, led us to propose a conjecture. But proposing conjectures based on computational evidence is something that mathematicians do very regularly, right? Like sometimes a conjecture is nothing else than I haven't been able to find a better number than this, so this is my upper bound or something like this, right? So what we're doing in that part of the proof is no different than what most computational mathematics has done for many decades, in my opinion. And we actually have a provable part to the whole story where we know a correct one must exist. The question is now just have we found it? But I'd like to give maybe a more general comment in that what has the machine learning done here? Machine learning wasn't the theorem prover. Machine learning did not pose the theorem, and machine learning did not pose the conjecture. All of those things were done by the human, okay? The mathematician. And what the machine learning has done is it gave you basically a bit of a magnifying glass to look at these complicated structures and figure out what are possibly very useful parts of it to analyze an otherwise intractable problem better. So I think regardless of whether or not the conjecture is true or false, we have discovered these dihedral intervals and these extremal reflections, which turn out to be, in the very least, super relevant in predicting it to a reasonable level of accuracy. So we've basically given mathematicians two new structures to play with, if that makes sense, right? So maybe what they do with these structures ends up being completely different from what we originally wanted with the conjecture. But I don't see... I don't see any danger in the particular results that we arrived at, because we've been very transparent about which part was done by the AI, which part was done by the human. And, if the conjecture ends up being false, in either way, the structures we discovered along the way have helped, pave the way for what comes in the future in this area.
If I can add one word, I wouldn't call it a magnifying glass, because it also gives a more general, a different point of view, a different vision. I wouldn't maybe calling it a magnifying glass is just limiting. I don't know. A magnifying glass just gives some more details.
Mm-hmm. Well, okay, the way it was used here was mostly a magnifying glass style where it looked at substructures inside the original structure. But yes, I agree with you that, in general, it can be more telling than just a magnifying glass, of course.
Okay.
Hi. I'd like to ask a question and directly in person. Computers are very useful now for mathematicians, and not only on this side of deep learning, but another trend is to use for computer assistant proof, like, for instance, Peter Schultz did for the grid unification theory and so on. Do you think that there is a connection between these two big trends now in computer assisted proof, or they are completely uncorrelated in the future?
That's a great question. I've thought about this a little bit. And what I would say is that they are probably complementary, to the extent that our approach helps you find the building blocks of what might go into a conjecture. And the theorem prover is a system that generally has all the axioms and setup given to it, and then it proceeds to try to find the proof, right? So you can imagine some idealistic future where, there will be some nice interface that allows you to take the insights from the magnifying glass or not magnifying glass, doesn't matter, and then shove those into a theorem prover to get the final, rigorous statement of the proof. So I think that could help us truly fully accelerate the procedure of not just searching for interesting structure, but also using that structure to arrive at rigorous proofs. And I feel like this could be quite transformative to mathematics when taken together, because usually a theorem prover doesn't have direct knowledge of the complexity of the objects it's dealing with, right? It relies entirely on the setup you give it. So yeah, I believe in the future these two orthogonal efforts could merge and could give a good interface. The reason why we haven't focused on theorem proving per se is that for many tasks of interest, I'd say theorem proving is an NP hard procedure, I would say. And machine learning models, at least for supervised learning, provably cannot perform well on NP hard problems unless NP and co-NP are the same, which as far as I know is a stronger statement than P versus NP. So very unlikely to be true. So basically, yeah, for supervised learning, we're focusing on those interesting heuristics that could be found in polynomial time, but the human eye is just not trained to properly see them when the examples get that complex, right? So maybe it allows us to have more immediate impact. But in the future, I could totally see these two efforts joining forces in one way or another.
Okay, thank you very much.
Okay, let's thank our enlightening speaker for today's seminar. Petar, thank you very much. Please stay with us for a few seconds while I give the next appointment to the talk by Daniela Di Serafino in 2 weeks' time for the AIM series, and the next week on Wednesday there will be another IAC general seminar at the usual time. Thanks a lot, and see you at the next iteration of the AIM series on artificial intelligence and mathematics. Thanks again to our speaker.
Thank you for having me.